you should be seeing chapter 4, quiz 1. And let me know if you can't, because full disclosure, Wiley Plus went through a major upgrade recently. I mean, almost a complete like source code level upgrade. And there's still, I'm not saying there's still problems with it, but they still kind of update it every now and then. So the functionality changes. And where that affects me is a lot of times I'm thinking stuff is available, but it's not, because it has been a bit of a moving target. So anyway, that's why you can let me know if you're not seeing something. Right now, you should see in Wiley Plus, everyone should be in chapter 4, quiz 1. What's the difference between chapter 4 and chapter 1? Chapter 4 and chapter 2. Chapter 4 is all about 2D kinematics, whereas chapter number 2 was all about one-dimensional kinematics. And you really can kind of boil these down into some basic categories. There's variable acceleration kinematics. There's constant acceleration kinematics. Variable acceleration is typically a job for calculus, as in stuff like velocity is dx dt and acceleration is dv dt. And the flip side of the coin says, well, if that's true, then I know v equals the integral of a dt plus so on and so forth. Whereas constant acceleration kinematics is oftentimes a job for the big five. The big five equations, sometimes they're referred to as the equations for uniform accelerated motion. That's a common term. But so it really is easy when you look at it like this, but what makes it maybe a little more challenging are the definitions. Plus, there still might be some of you who are less than rock star level with calculus. And you don't need to be a rock star with calculus, but you do need to be proficient. You do know how to do sort of garden variety, straight ahead, derivatives and integrals. And I will post a refresh, a calculus refresh. I had a student ask about that. So if you just need a refresh, I will give you, I think, the best resource. You could always go to Khan Academy or anywhere else, but what I like about the resource that I'll give you is it's directly a Wiley Plus. It comes directly from Wiley Plus, which means it's exactly at our level. It uses the terminology we use. It's focused on physics, etc. All right, so let's just dive into it. Chapter 4, quiz 1. This is kinematics. And there's some new stuff here, unit vectors. All right, so anyway, I'm gonna just start. Number 1, kinematics analysis method to the rescue. Again, it's good as a scientist or engineer. You've got to you probably do already like methodologies, procedures, standards, structure. You like best practices. You also like to innovate and be creative, but you like all of that stuff. So KAM stands for kinematics analysis method. This was mentioned in your lecture video, and it's referenced on your green sheets. And this is one of the 3 methodologies in this course. There's going to be kinematics analysis method, there's going to be force analysis method, and energy analysis method. So, I mean, in general, it sounds like a Fight Club, the movie Fight Club quote. Like, in general, you want to have enough methodologies to cover all the scenarios but no more. It's like the first rule of the Fight Club is there is no Fight Club. The first rule of methodologies for me is everything should be covered by a methodology to the minimum extent possible. Meaning, I think the worst thing I could do is give you 12 different kinds of methodologies for all of the types of kinematics problems you might be. And I think the textbook sort of does that, I think, or that's a common practice. Well, for this type of kinematics problem, use this methodology. For this type, use this methodology. So I like the idea of having a methodology, but I really like the idea of universal methodology. So let's start with the drawing. That's part of the methodology. You have to cough up a drawing. This looks like 2-dimensional kinematics. How do I know it's 2-dimensional kinematics? Because it references I hat and it references J hat. We'll talk about I hat and J hat, but for now, you just need, and you should be following along. You need to just make a 2-dimensional two-dimensional graph. Not like that. You need to make a two-dimensional graph. Actually looking like this, because this is two-dimensional motion. So here, Cartesian coordinate system. Cartesian coordinate system, let's see. Here's my object. I'm gonna represent my object as just a dot at the origin, because that's what it says. Okay. One of the other keys to problem solving is a particle leaves the origin. So here's my particle, there's the origin. The origin is sitting here at coordinate 0, 0. So 0, 0 meters, that is the origin. That red dot is my object. And according to my additional specifications, this is just like, I always think of this as just like an engineering specifications document or a design document, or maybe even closer to me, a testing document. It leaves the origin with an initial velocity that's given. So let's draw the initial velocity. All right, so I'm going to use this color right here. So here's my initial velocity. Ready, set, go. Okay, this is the initial velocity according to the specification. It says this initial velocity is equal to 7.36, and then it says I hat meters per second. So I think some of you have probably learned about I hat, but I don't think I don't assume anyone's known about I hat. So this is new and introductory. I hat is a unit vector. It's a unit vector that is directed, unit vector in plus x direction. That's what the I hat unit vector is, plus x direction. So brand new terminology to maybe some of you, maybe not to all of you. And you know what? I hat is a unit vector in the plus x direction. And unit vector means the following. Unit vector means the magnitude of this vector. This is how you indicate magnitude. These vertical absolute value symbols, that means magnitude. The magnitude of that I hat unit vector is equal to 1. So if my initial velocity is 7.36 meters per second in the I hat direction, I actually would read it as, I would read it like this. It's 7.36 times 1 meter per second in plus x direction. That's how I look at this unit vector. So whenever you see something like this, 7.36 I hat meters per second, I'm going to say it's 7.36 times 1 meter per second because of that unit vector in the plus x direction. Again, that's magnitude of unit vector I. That little hat, that little up caret means it's a unit vector. So that's my initial x direction. So I'm going to just stay true to subscripting Vx initial. So this is a double subscript. I have V for velocity, subscript X for X velocity, subscript I. So V sub X sub I is read as initial X velocity. What else? I know my acceleration. I have acceleration data. So let's go ahead and talk about acceleration. I'm going to use a different color for acceleration. My acceleration, let's see, it's two-dimensional. So negative 4.28, got it. And negative 1.16, got it. All right, that looks good enough. Sorry, good enough. So I'm going to write this. This is AX equals negative 4.28 I hat meters per second squared. And this would be A subscript Y equals negative 1.16 J hat meters per second squared, which means I better go over here. J hat, when this thing called J hat is a unit vector, just like I hat was a unit vector, which means its magnitude equals to 1. J hat is a unit vector in the positive Y direction, in the plus Y direction. So this is our grand introduction to unit vectors. The magnitude of j hat is equal to 1. So again, the way I read this number right here, if I'm going to translate this, I would translate this as negative 4.28 times 1 meter per second squared in x direction, and that negative stands out. So this is why you can have unit vectors going to the right or going to the left. If you're talking about x, if I'm talking about y, a unit vector can go up or down based on this sign right here. But it's some number, 4.28 in my case, times, and here's the unit vector. This is my j hat unit vector, or I'm sorry, my I hat unit vector. Okay, so that's it. That's a sub x. That's a sub y. I guess that's in terms of the givens. That's a good start. So now what you need to do, back to kinematics analysis method. Let's see, we have a fully labeled drawing. Fully labeled, which means subscripted. We have a fully labeled drawing with all the subscripts. And then the other thing you're going to need is a 6-column data table. All of this is just going to be standard operating procedure. And you should practice this way. When you do homework problems, do it this way. Otherwise, when you do an exam, everything is new and spinning. 6-column data table. So here's the 6-column data table. Step 1, step 2. I'm going to do my initial x position, my final x position, my initial x velocity, final x velocity. These are all of my kinematics variables. So how do I know when to stop? Well, at 6, there are 6 kinematics variables that you have to worry about. If you can specify all 6 of these kinematics variables, you completely are describing the motion of an object. Now I have to do the same thing for y because I have 2-dimensional motion, y initial, y final, vy initial, vy final, a sub y, and t. And now what do I know? This is where you just sort of fill in the blanks. I know it's leaving the origin, so this would be 0 meters. This would be 0 meters. I know my initial velocity is 7.36. I can put that here. 7.36 meters per second, because that I, again, this I means x. And you might wonder, you might be thinking, why don't they just say x? And you'll see. My acceleration, a sub x, is negative 4.28, negative 4.28 meters per second squared. Got it. Got that. And then what about, where do I put that? Negative 1.16. That's my y velocity. That's okay. Negative 1.16. Negative 1.16 meters per second squared. That's my, I said y velocity. I should have said y acceleration. All right. So I have found a home for everything. 7.36 has a home. I found a home for it. The origin, found a home for the origin. I've got a home for a sub x and for a sub y. Now what else? Before I turn my back on this table, what else should we worry about? And the answer is read the question. Let's read the question a whole bunch of times to make sure we squeeze out everything from it. A particle leaves the origin. This is my initial velocity. Constant acceleration. You know what that means? Ta-da. Constant acceleration means you are looking at this. You're looking at the big 5 equations because the acceleration is constant. So let me fix that. Constant acceleration means big 5. It's the kinematic analysis method with the big 5. So I'll just write that. It's kinematics, and it's always kinematics analysis method along with the big 5. That's what constant acceleration is referring to. Now here's an interesting sentence. When the particle reaches its maximum x coordinate. So this particle is moving in the x direction and the y direction. And you know, I can tell just by looking at what I have here graphically, I can sort of get a feel for how my particle's moving, because my particle starts out moving in the positive x direction. You can see that. Vx initial is 7.36, but immediately it starts to slow down in the x direction and speed up in the negative y direction. So my guess is, it's more than a guess. Here's how I believe this particle is moving. It's moving, ready, set, go. It's probably moving something like that. And how do I know that? Because again, at time equals 0, it comes, it's as if you shoot this red projectile out of a cannon. It starts to go immediately to the right, but then there's a gust of wind that pushes it down and to the left. And I'm saying this gust of wind seems to be pushing it down because of this negative x acceleration, that negative I hat acceleration. And it seems to be pushing it in the negative y direction because of this. Negative j hat means negative y direction. So I believe my particle is actually following a path like this based on all of the aforementioned evidence. So at some point, this particle is going to reach a maximum x coordinate right there, for example, right there. That's a maximum point. So right here, I can say this, whatever this x coordinate is right here, whatever this x coordinate is, maybe I'll do it like this. Okay. Whatever this is x, whatever that, I'm going to call that final x. That's going to equal the maximum x. And you know what else I can say? I can say this. At that final x position, final in the context of how we're looking at things right now, at that final x position, I've attained, this particle has reached a maximum x coordinate, because then again, it starts to reverse itself. And at this point, you know what I can say? I can say Vx final equals 0 meters per second. So that's huge. This red particle starts off going fast in the x direction, and then immediately after launch, it's feeling a gust of wind that's sending it downward and to the left, or it's trying. The gust of wind is basically accelerating it downward and to the left. So I'm going to add to my data table x final when the particle reaches its maximum x coordinate. Well, this is going to be, I need to find out that coordinate, but I do know when it reaches that final x position, at that moment, its velocity is 0. Because it momentarily comes to a stop in the x dimension, not in the y dimension. None of what I'm saying here applies to the y. So I've got a lot of good stuff here, and I'm going to put a question mark. All right, and that's it. That's it for my x data table. So I've just spent an enormous amount of time talking through all of this stuff. And this is time well spent. So I'm pretty confident about my x coordinate, or my x data in my 6-column data table. What about the y? Let's see, because I need to find out the velocity at this point and the position vector. The position vector is going to look like this. I'm just going to draw the position vector right now. I need to find this brown vector. This brown vector is known as the position vector. Position vector starts from the origin and it terminates at the location of this object. And I'll give it a name. I'm just going to call it, for lack of a better term, r hat. So this is not r hat, r vector. I need to find that position vector. Okay, so that's it. That's it for my x data. What about my y data? When the particle reaches its maximum, so what else can I say? Y final, I guess I got everything. Everything needs a number or a question mark or a dollar sign. So I got a number for y initial. Y final, I got to find that. I got that. That's part of my position vector. So I must find y final. Vy initial, 0 meters per second. How do I know it's 0 meters per second? This is your initial velocity, and it is given only in terms of I hat. And I hat, once again, corresponds to the x direction. Okay, so 0. Vy final, I don't know, and I might not. Oh, I do care, I think. When the particle reaches its maximum x coordinate, yeah, this is a $sign. All right, there you go. So just spent, again, a ton of time making a drawing and making this setup table. And you're thinking, here we are, whatever, 15 minutes in, and you're still not, you're still not jotting down equations. I mean, and I know the urge. I know the urge says to just start with equations, just start spewing out equations at all costs. If you don't understand something, doesn't matter. You just got to keep writing equations. I know that tendency, and here I am not writing any equations. And for good reason.
Professor?
Yep.
Sorry to interrupt. For Vy final, we put a $sign. What was the explanation behind that again?
Vy final, because it's saying when the particle reaches its maximum x coordinate, what is its velocity? So that's actually a very insightful question, because if you need to find its velocity, that means you have to find Vx final as well as Vy final. And you already know the Vx final. Vx final is going to be 0. So the only velocity you have to find now is the y velocity. So that's a very good question.
All right, thank you.
Why is the velocity 0?
Say again.
Why is the velocity 0 for VXF?
Because this is a turnaround point. VXF, when this particle is going along. So I gave you my thought process explaining why I believe this red particle is following that green path. This is a turnaround point. This is the turnaround point for the x coordinate. Turnaround point for x motion. That's why. Because again, as soon as this particle leaves the origin, it immediately is subjected to an x velocity that's trying to go in the negative. So this x acceleration is trying to slow it down. It's going in the positive x direction. That this negative sign means it's going to slow down, and it's going to slow down. It's going to stop, and then it's going to continue along its way in the negative x dimension. And then as far as the y, there's no turnaround. There's no evidence of a turnaround point in the y dimension. So let's see, x, I'm just going to go through before I go on. X initial is 0, y initial is 0, because I'm starting from the origin. I got to find my xf and yf, because this position vector, I could write the position vector like this. This position vector is going to be some x final times I hat plus some y final times j hat. So that's why I need to find xf and yf. This is given. 7.36 is given. 0 is implied. 0 is not given. It's implied because my initial velocity only has this I hat indicator, which means that's only x velocity. XF is 0. So I talked a lot about why this slows to a stop, hits a turnaround point, and then reverses itself. On the other hand, my y velocity at that point is I don't know, and I need to find it. And I'm given this as my x acceleration and that y acceleration. And as far as time, I don't know anything about time. Or do I? Better double check. No, there's no mention of time here whatsoever. So I'm done with this exhaustive setup diagram with vectors and subscripts. I'm done with my kinematics table. And then it's back to the kinematics analysis method, which now says play the big 5 game. So playing the big 5 game means which big 5 equation contains the variable you need to find with all other variables known. And this is why for every hour we spend together in class or on Zoom, you spend probably 2 to 3, sometimes less than 2, sometimes more than 3 hours practicing. Because the only way this is going to sink in is if you just practice. I mean, you got to learn it initially and then you have to practice. So let's see. I got $3 signs. I have to find these $3 signs. So without really thinking hard, because a lot of this is at first it'll be a guess and check. I'm going to try this. I'm going to try. There's one of the big 5 equations that says x final equal. No, I don't want to try that. Maybe I do, but there's one of these equations from your green sheets. You at this point, you are literally kind of raising a red alert if you're not really familiar with those green sheets. There's an equation in the green sheets that says VXF squared equals VXI squared plus 2A sub X final minus X initial. This was derived. So if you guys are on a path of science or engineering, you have to understand the derivations. You can't just be an equation operator. You just can't copy down equations that were derived and plug numbers in. That's not the path you're on. That is not the path of a scientist or engineer. So the reason I'm choosing number 4 is because there's no time variable here. So I don't know time, but I'm feeling okay. I'm feeling okay not knowing time because this equation here, this is one of the big 5. There's no mention of time here. And yet here's my dollar sign right here. All right, so it's something. That's something. All right, so let's get one of the dollar signs answered by solving number 4. So I'm going to try. Let's see. VXF squared. According to my data table, I have 0 squared equals my initial X velocity, 7.36 meters per second squared plus 2 times A sub X. According to my data table, A sub X is negative 4.28 meters per second squared times XF, that's my dollar sign, minus X initial, which is 0. Okay, let's solve for X initial, or I'm sorry, X final. This is one of our $3 signs. Let's figure it out. Okay. Interesting. I get the answer of 6.328. Dimensional analysis. I got it. I have to do dimensional analysis because you need to do dimensional analysis because that won't be an option. So from a dimensional point of view, I have 0 equals meters squared over seconds squared. So I'm squaring meters, I'm squaring seconds, plus this is meters squared per second squared, meters over seconds squared times X. So, okay, yeah, so I can see this. I would just say X equals meters squared over second squared times second squared over meters. All right. So I'm doing the dimensional analysis. Now I'll talk through this maybe more as we go on. But if I do the dimensional analysis, I do get meters. And technically speaking, that should be the first thing I do because I could have just wasted a lot of valuable time. Because if I did this dimensional analysis and I did not get meters, that means I have a mistake going on somewhere. So I should have done the dimensional analysis first. And the calculator part second. I'm going to do this. SICM, which stands for store in calculator memory location. Store alpha A. So that's that for this dollar sign. So let's see, what can we do right now? It says when the particle reaches its maximum X coordinate, what is its velocity? Don't know. What is its position vector? All right, so we can say something about the position vector. No, I'll keep going here. Number 7. Here's the position vector. Visually, I've shown what our vector looks like. It equals, again, some X final times I hat plus some Y final times J hat. So I actually know this component of this vector. If I look at this vector, I'm going to erase this. Well, I'm going to redraw it. Maybe I should say. Here's the position vector that I'm spending a lot of time talking about right here. I'm just going to redraw it here, just so it's easier to see. This is just a copy and paste of the position vector. It does have a name. It's R vector, and it has 2 components. It has an X component. This is why we study trig. it has an X component that looks like this. And it has a Y component that looks like this. And label those. So this is Rx equals X final I hat. And this is Ry equals Y final J hat. So that is this is a great visual. And it's a chance to remember how we deal with vectors. So if I'm going to write from a vector point of view, this is how I represent our vector. Our vector is what happens when you take this Rx vector and then vectorially or graphically add it with this Ry vector. And then to go even a step further with this, Rx is the same as xf times I hat plus Ry times J hat. So from a vector point of view, if you need to follow vector rules, which means you go in you adhere to a very specific criteria. If I want to figure out what this vector is in terms of its underlying components, then I basically say, okay, well, what is the X component? This is an engineering thing, break things down into little chunks. What is this X component? Okay, got it. What is this Y component? It's right here. That's it. So graphically, this blue vector equals these two yellow vectors added together. And that's, well, let me draw it like this. Yellow vectors. Okay. So that's vector. This is a vector operation. You're looking at it. This is the graphical representation of the R hat vector. And then this is the vector representation here. This is the unit vector representation. So what I'm circling in green here is represented precisely by this visual right here. So there's a lot of new stuff going on. I understand that. Practice makes perfect. Okay, so number eight, because I guess I'm answering part B first. What is its position vector? Its position vector is, I got the, I'm not quite ready for that because I have XF. So I guess I'll just dribble it out. Equals XF 6.328 I hat meters plus some Y final value. Now I need to find this variable right here. So one down, one to go in terms of the position vector. So I'm going to go back to my Y. I'm going to play the Big Five game again. And it really is this. I mean, there's a certain number of rules, but once you master these rules, it's like cards. Once you learn the rules, then it's all about strategy and innovation. So play Big Five game. Play Big Five game to find Y final. Okay. And now I can tell there's a problem already. So I'm going to write down number 10. Too many unknowns. Too many unknowns. Because why am I saying too many unknowns? Because look at this. Look at this says 0. This says 0. I don't know this, and I don't know this. So of these 6 values, of these 6 columns, I only know one. I only know the acceleration. So this is where you now you can get creative. Now you can sort of slingshot to the other side of your brain and get creative. And then I'm going to say, aha. Aha, what? Well, I'm going to say, aha, find time from X data. I know, and this is a common tactic, and now you know it. I mean, maybe you could have figured this out by yourself, and that'd be nice, but one way or the other, either you figured that out by yourself or I told you, but now once you know it, you know it. This is a very common tactic. So, okay, find time from X data, Big Five game. So if I play the Big Five game, at this point, you would look at your green sheets And you would certainly remember that there's a lot of derived equations, and I'm going to look at specifically this big 5 equation. I'm going to look at, what should I look at? I guess based on what I know, I'm thinking of, I'm going to look at Vx final equals Vx initial plus A sub x t. And again, just to be paranoid here, you might be asking, where the heck did this come from? And if you're asking that, you made the decision to not spend any time on the green sheets or the lecture videos, which is already cause for concern. That is an approach that's just not going to work. But it's not too late. It's not too late. If you want to get great advice about procrastination, get it from a procrastinator. And I have a natural tendency to procrastinate, but I've learned to overcome it. Solve for t. Solve for t. So let's get the time. Let's get t. Looks like it's going to equal vxf minus vx initial over a sub x. So with numbers, I'm just going to my data table. Vxf is 0 minus my initial velocity minus, for me, it's 7.36 meters per second. That's my numerator. My denominator is negative 4.28. Negative 4.28, referring to my data table, negative 4.28 meters per second squared. Now I'm actually going to do the right thing. I'm not going to go to the calculator just yet. I'm going to do dimensional analysis because it is an exam requirement. So as far as dimensional analysis is concerned, in the numerator, I have meters per second. In the denominator, I have meters per second squared. What do you get? What does that simplify to? That will simplify to meters. So done. My dimensional, except I said that wrong.
Seconds.
Seconds, thank you, thank you. That does simplify to seconds. Okay, so I'm feeling good. I'm feeling good because I'm getting seconds, and I want seconds because I'm trying to solve for time. So now let's get a number.
I'm sorry, that negative 4.28, that's the I hat or J hat in your given acceleration.
Let's see here. I am looking because my statement here said find time from X data. I'm looking at my X data because I know so much of it. So here is my X data right here. All of this is my X data. So when I say I'm going to find this time value from X data, I'm using all of that X data. So, right. That's why those numbers are what they are, because again, that's why I kept saying, I'm going to get these numbers from my data table, which means you better have a data table. So let me zoom out. Hopefully that's not too small. Okay. So we got seconds. Let's get a number. 7.36. 7.36 divided by 4.28. I have a number. Store alpha B. And again, that's 7.36 divided by 4.28. Okay, so I get a number. So the time. This particle reaches that X turnaround time at, for me, my numbers will be different than your numbers, at time equals 1.719 and some change seconds, whatever. There's a lot of decimals to the right of there's a lot of numbers to the right of the decimal place. I'm just going to store them all, keep all the precision, store in calculator memory location B. That's that. Now,
how do you do that store thing on the calculator? What buttons are you pressing?
it depends on what calculator you have.
I have a TI-84.
Yo, Leon, if you go to like the bottom left where the on button is, there should be a key right above it that says stow.
Oh, I see it.
Yeah, just take a number, just hit stow, and then alpha will like
We know when this particle hits that turnaround time in the X dimension. Now let's go ahead. Here I said play big 5 game to find Y final. Too many unknowns. And I'm going to say, okay, phew. Try again. Try again because I know time. So play the big 5 game, which is it's a guess and check game at first. Which one of those big 5 equations for uniform accelerated motion contains the variable you care about with all other variables known? And just to sound again repetitive at this point, you should recognize these equations because you should have lived through the derivation and used, I think, some of them already in the homework set 1. But I'm gonna try this. I'm going to try. I'm after y final. I'm going to try y final equals y initial plus vy initial times t plus 1/2 a sub y. And just as I'm writing it down, is there a simpler one? What about, or maybe I'm thinking this, y final. I remember this from the big 5. And I remember just because I've seen them before, but your point is to recognize, you don't have to have them memorized. You just know where they live and you have to know how they were derived. I'm thinking maybe this 1/2 y initial plus vy initial. This is another of the big 5 equations that were derived. So the second one looks easier. Do I know vy initial? Yes. Do I know vy final? No. So nope. I have to use, so this is nope for that one. So I'm going to go barking up this tree. Y final equals y initial, which is 0 meters, plus vy initial, which is 0 meters per second, times time, which is sitting there in memory location B, isn't it? Where did I put my time? Yeah. Time is sitting there in memory location B, and that's just going to equal 0, plus 1/2 a sub y. According to my data table, I better use negative 1.16 meters per second squared times t squared. That's it. That's my setup. You would do the dimensional analysis. You know how to do that. We'll do some more of it, but let's get an answer here. 0.5 times 1.16 times alpha b squared is not right because I didn't store my time. So let's see here. I did not store my time. Negative 7.36 divided by negative. Store alpha b. Now try it again. 0.5 times negative 1.16 times alpha b squared negative 1.7 some change. So this is what I get. My y final equals negative 1.715 and some change meters per second. Okay, so I am completely done with part B because you need to enter the I hat component. What is the x coordinate of this red particle when it hits that turnaround point? And the answer is right here for me. The answer is 6.328 meters. So that's why this they've rounded it for display purposes is 6.33. But this is my I hat number for final position. This is my J hat number for final position. So Y final, I guess I could write it like this, J hat. So I'm going to use the same purple marker. This is the Y coordinate. And because I'm referring to it as the Y coordinate, it does get this J hat vector. J hat means Y. So you can see here on my answer key, yeah, I got the right number and I am specifying it as a J hat vector. So this is the X result. This is the Y result. So I'm completely done with the final position. Lots of new stuff here. So I'm taking an enormous amount of time just because I want to go really, really carefully, like really intensely through what is a unit vector, How do you deal with unit vectors? Let's practice this big five. I'm sorry, let's practice the kinematics analysis method. But I am completely done with part B. Now I have to just go back and do part A. So number 17. The only thing left to do is part A said, what is its velocity? What is velocity? And again, I'm going to write it like this. What is the velocity? Just so we don't lose track of where we came from. What is the velocity at x equals x max, the turnaround point? I know the coordinates. I know the x velocity. This is vxf equals 0 meters per second I hat. And I know that's 0 because it stops and turns around. Otherwise, it couldn't ever reach a max. As soon as they told you you've hit a maximum x coordinate, you know, aha, I must have turned around in the x dimension. So now I just need to find VYF. That's what I'm after now. Let's play the big five game. Big five game. And that goes as follows. Which of the big five equations contain the variable I care about with all other variables known? And I'm going to guess this. I'm going to guess VY final equals VY initial plus A sub Y times T. This is one of your big five. It was derived. You should absolutely know the derivation. If you are, again, following the path of science or engineering, you need to know these derivations. And this is pretty straightforward. This was derived for you. I guess that's just plug and play because I can just see that the answer is my final Y velocity. I know my final X velocity is my initial Y velocity, which is 0. So I'm referring to this Y data. That's 0 meters per second. Right? Plus the Y acceleration, which according to my data table is negative 1.16 meters per second squared times time. And time is sitting here in memory location B. Like that. So this is why you store things in your calculator. Dimensional analysis has to come first. So from a dimensional analysis point of view, VY final equals, I have meters per second squared times whatever I have, times this time value. So what do you get when you get meters per second squared times seconds? Because again, all of this is meters per second squared. This is time, and I am getting meters per second. So I do get meters per second from a unit point of view. From a numerical point of view, I'm going to do negative 1.16 times alpha B, or negative 2. VY final equals negative 2 meters per second J hat. That J hat again means this J hat is going along with this Y. Y and J hat go together. So I am completely done. I'm going to circle this in purple. This is my final Y velocity. This was my initial X velocity, which was 0, which is right here. My final X position was given to you in step 6. My final Y position was given to you in step 16. So done. A lot going on here. Yep. Question.
Could you extend it? I can't see if I got it right. It won't let me submit
Okay,
anymore.
let me do that right now. It is now 1:56. So I spent just under an hour talking about this just because there's a lot of new stuff. Okay. And chapter 4, quiz 1. Chapter 4, quiz 1 will now be extended to, I'll say 2:15. Give me a second. Okay. And as of right now, it's refreshed. Go ahead, get the right answers, ask questions. If I need to extend the time, I will. Just don't get preoccupied by getting the right answer. You're going to get the right answer.
Why is this?
The question is, are you going to get the right answer and learn the methodology and the tactics and strategies? Let me take a look at how people are doing.
Why
This
did that?
is chapter 4, quiz 1. This is a pretty heavy problem. Don't let me give you the impression, oh, this is a no-brainer. Anyone? No, this is definitely some heavy lifting, but that's why we're taking an hour. Oh, grades. Okay, chapter 4, quiz 1. Basically, no one's done. So you guys need some more time. Here's what you need. You guys need more time, or if you're stuck, you need to ask questions. I can give you more time. Well, you kind of need to indicate. Well, I know right now I need to give you more time. If you're stuck, you have to speak up because I won't know. If you don't speak up, I won't know if you need an assist with anything. So let's do this then. It's 1:58. 7-minute break is 2:05. I'm going to write this down on your screen. See you at 2:06 because that's a nice little break. Number 1. Number 2, it gives you a chance because nobody's asking any questions. That just to me implies that you just need a bit more time, which is totally fine. So there, between 1 and 1:30. So I will see you guys at 2:30. It is now 1:50. I'm sorry. I will see you guys at 2:06. Or chapter 2 is our next kinematics challenge, quiz 4. I'm sorry, I keep saying that wrong. Chapter 4, quiz 2. There it is. There it is. Ooh. Yet another 2-dimensional kinematics problem with unit vectors. So this a major theme of today is unit vectors. And if it's new, I know, like everything else, if you're like me, if it's new, it's uncomfortable. So I understand that. And again, this is where you're, in general, this is how it works out from an average point of view. You should be spending probably between 1 and 2 hours on physics 4 or 5 days a week, in addition to your class time. So ask yourself, have you been doing that? Have you been averaging about 1.5 to 2 hours or 1 to 2 hours, 4 or 5 days out of 7 on physics beyond just the classroom? So let that be a sanity check for you. And it's not unique to physics. That's a common rule of thumb. In fact, that rule of thumb gets more intense the higher you go in the food chain. So here we have another 2-dimensional kinematic situation. How do I know this is 2-dimensional kinematics? Because right away I see I hat and J hat. So here's evidence of X motion. Here's evidence of motion along the X-axis, maybe in the positive or negative or both X, and J, that's Y. I mean, that's the Y-axis. Okay, so this is for sure 2-dimensional kinematics, not 1-dimensional, but 2-dimensional. So again, it's kinematics analysis method to the rescue. And then one of the first questions is this constant acceleration or is it variable acceleration? And you know what? I'm not sure I know at this point. So let's just start doing the read through. Number 1, let's read through the velocity of a particle moving in the XY plane. So let's just solve every problem, including homework, as if it were an exam problem. This is moving in the XY plane. So this is your X coordinate. This is your Y coordinate. This is a Cartesian coordinate system. A particle is moving in this plane. So just think of Mars Perseverance rover or robotics or mechatronics or cruise control. This is program motion. And I have a particle. All right. So All right, so what to do? I guess my particle, this is my velocity with v in meters per second and t greater than 0 at 1.14 seconds in the unit vector notation. What's the x component and y component of the acceleration? Okay, let's do that. So I'm going to draw my particle right here. They never really said where this particle is starting from. So you know what? Because they don't tell me where this particle is starting from, I'm just going to take the coward's way out and put it at the origin. It's not really the coward's way out, but I'm going to take the easiest path. So this is what's going on with this particle from a velocity point of view. I have some x velocity component, so I'm going to draw that. Here's my x velocity component. And I'm just going to label that as some x velocity component. So this is going to be Vx. And then it's going to have some y velocity component. So I'm going to label that as just some y velocity component. I guess let me change my thickness here. Okay. Vy. All right. So, and now here's the thing. Look at this representation. This is called parametric representation. So the way I can say a few things about how velocity appears here. This is velocity. The velocity of this particle, velocity is expressed in parametric unit vector notation. So when I look at that, that comes to mind, unit vector notation. Why am I saying unit vector notation? That's easy. I'm saying unit vector notation because you can see an I hat, which signifies X dimension. And I can see J hat, which signifies Y, the Y dimension. So unit vector notation is a no-brainer because, again, I can see an I hat and a J hat. Parametric means basically I have a formula for X and a formula for Y. Basically, you can say I don't have a formula for Y, but I basically have a polynomial. I have a math equation that's keeping track of my X dimension and another polynomial that's keeping track of my Y dimension. So fancy sounding term, parametric unit vector notation, but now you know why it's referred to unit vector, and parametric just means, hey, I've got a fancy, and again, you as a robotics engineer, mechanical engineer, programmer, software engineer, you do this. This is for you. You do these algorithms. Okay, and now we all do these algorithms. All right. So at 1.4 seconds and in unit vector notation, what's happening? So at 1.4 seconds and in unit vector notation, what's the X component and Y component of acceleration? Let's do that. All right, so number one, number two. All right, so, well, A sub X, this is a job for calculus, equals the first derivative of velocity. This should be very now familiar to you because of the green sheets, because of the lecture video, because of what I hit on this last Tuesday, last Thursday. So for now, you guys kind of have to be off the launch pad in terms of basic definitions like this. So let's take the first derivative with respect to time of the X velocity. This is the X velocity. What I'm circling here, this is Vx. So I can take the first derivative of 5.5 t minus 10 t squared. I don't need to write down I because I know I'm talking about the X component. That's what the unit vector I hat is telling me. And I know how to do derivatives. So if I take the first derivative of this expression, and again, this whole expression here, this whole beast right here is Vx based on what you were given. That
Isn't it 5t squared?
5t squared, you're right. Good catch. 5t squared. Very helpful. 5t squared. All right, so if I take the derivative of that, it's going to be 5.5 minus 10t. So this is variable acceleration. How do I know this is variable acceleration? Because it has a variable t in this expression, meters per second squared. So number 3, at time equals 1.4 seconds, a sub x equals 5.5 minus 10 times 1.4 seconds. 1.4, 5.5 times 10 minus 1.4. Calculator says 5.5 minus 10 times 1.4, negative 8.5 meters per second. Negative 8.5 meters per second squared. Almost made a dimensional analysis mistake. All right, so got it. The answer to the x component, the answer to A is A sub x equals negative 8.5 meters per second squared in the I hat direction. So it's going in the negative x direction. All right. What about number 5b? Here's the y component. The y component is A sub y equals the first derivative of velocity with that subscript notation, dv subscript y dt. So now I have to take the first derivative of v subscript y. Here's v subscript y. V subscript y is right here. Let me erase. Just like that was v sub x in front of my I hat symbol. There it is. This is oh, come on. This is v sub y. V sub y equals 9 meters per second j hat. So I just need to know how to take the derivative of 9 meters per second. I don't need to drag along that j hat. And the answer is 0, equals 0 meters per second, because it's a constant. 0 meters per second squared. And that is A sub y. A sub y equals 0 meters per second squared j hat. So feeling good about part A and B. You guys for sure, though, keep assuming I'm going to make a mistake and keep asking questions. That's A sub x. In unit vector notation, this is A sub y. In unit vector notation, part C, when, if ever, is the acceleration equal to 0? I don't know. Let's do this. All right, so number 5, number 6. When, if ever, is acceleration equal to 0? Well, let me back off on number 6. Let's talk about what we're looking at here. In general, you guys, I can write it like this. In general, I have an acceleration. And my acceleration has some x component and some y component, exactly like I'm specifying here. A sub x I hat plus A sub y j hat. So if I wanted to express acceleration on a Cartesian coordinate system like this, I could say, all right, well, I know that, yes, I have an x component. Let me just draw, this is just general. If you're wondering, where are these numbers coming from? I'm just sort of like being general. In general, I might have an x component of acceleration, and then I might have a y component of acceleration. And in fact, you always have an x component and you always have a y component. This is a y j hat. This is a x I hat. And you guys all remember the Pythagorean theorem. Here's what the Pythagorean theorem causes you to do next. First tail to last head right here. So this is it. This green vector This green vector that I'm labeling A, vector A equals the net acceleration. Net acceleration. I have two components that comprise that acceleration. I have an X component and a Y component. And because I know X and Y are always perpendicular, this is a right angle, and I know Pythagorean theorem, and I know sine and cosine and tangent. So this is what I'm after. I'm after this net acceleration. And the question says, when, if ever, is the acceleration equal to 0? So let's go with that. I gave you just sort of a general backgrounder on the acceleration vector. Let's keep going with this specific question. Okay, number 7. Well, the vector A, once again, I'm just going to do this for repetition purposes. It's going to be some X component I hat plus the Y component J hat. And now let's get super specific. What's the X component of acceleration? Ready? The X component of acceleration is, as I worked out before, 5.5 minus 10t I hat. Where did this number come from? Because I am saying this is A sub X. And this A sub X came from right here. This was A sub X. So I'm just copying and pasting from number 2. There's A sub X, 5.5 minus 10t. What's A sub Y? Here's A sub Y plus 0. I'll call it plus 0 J hat. And then I should not lose sight of the fact. So this is A sub Y J hat. And yes, I know collectively that I do have units of meters per second squared. So I can factor out units just like I can factor out anything else. So now the question is, when does this ever equal 0? So when does all of this equal 0? And you can see now this becomes an easy algebra situation. Number 8. It equals 0 when 10t equals 5.5 or t equals 5.5 over 10 seconds equals 0.55. With my numbers, your numbers will be different. So this is definitely a lot going on. There's a lot of new stuff here, which again is why we're spending an hour per problem, but it's good. It's good unless you're not understanding something and not asking questions, but I'm assuming you're comfortable with all of this. This is when, at this time, at t equals 0.55 seconds for me, my acceleration is 0, my net acceleration. Because again, we have variable acceleration. Last part, lots going on here. Okay. D says, when does the speed, at what positive time does speed equal 10? All right, so number 8, number 9, part D. When does speed equal 10 meters per second? There's a difference between speed and velocity. But let's talk about velocity to start with. Same conversation. My net velocity is going to be whatever the x component is, I hat, plus whatever the y component is, j hat. And you have a picture right here. So my net acceleration, it's the perfect position for this picture. My net acceleration looks like this. Okay, this black vector. This black vector is called vector v. This is my velocity vector. So if you look at this visual, well, I know this is a right angle because I know x and y are always perpendicular. But if I look at this visual right here, this visual is identical to this statement right here. because you always sort of just stack things out like that. This equation is saying, hey, your velocity vector, here's what you do to find this velocity vector. You take your x component, got it, and then you graphically add it to your y component, which I'm doing here. And when you're done doing that, because in some cases you might actually do this a bunch of times, I might have x and then y and then z, or whatever you do, you just go, okay, this arrowhead, this tail right here to that head, and then this tail to that. So you just play the tail to head. In fact, I always think of this as the tail to head method, tail to head method. So it's tail to head, tail to head, tail to head. And then when you run out of heads, you just say, okay, you're done. So tail to head, I'm done. And then you go first tail to last head. This is just a graphical rule. Anyway, that's what I get. This black vector is the combination of an x contribution and a y contribution. All right, so now we have to talk about when does that speed equal 0. So let's go with this. I'm going to remember Pythagorean theorem. So step 11. Well, the magnitude of that velocity equals speed. Magnitude of velocity equals speed. And then I'm also going to remember what Pythagorean theorem says. What is the magnitude of this vector? The answer is it's whatever the Pythagorean theorem says it is. So the magnitude of this velocity vector, in addition to being known as speed, let's just use Pythagorean.
Damn.
Let's just use Vx squared plus Vy squared square root. That's Pythagorean theorem, because you know Pythagorean theorem says V squared equals Vx squared plus Vy squared. So that's all I'm doing. That's all I'm doing with step 11. Step 12 says, alrighty then, when does that equal 10 meters per second? So here's the speed. 10 meters per second must equal Vx squared plus Vy squared square root of all that. What's Vx squared? Here's Vx squared.
Is it off?
Guys,
Wait, I don't want to be in the camera view.
yeah. Okay, let's just mute Oliver, because Oliver, you're having a yourselves. So let's just mute everyone. Okay. Good. All right, so Vx is given to us as follows: 5.5 t minus 5t squared. That's Vx. Got it. I need to square that. Plus Vy squared. Here's Vy squared. 9 squared. Vx squared plus Vy squared. And then square root the whole thing. All right, so let's make sure. Sanity check time. This is my speed. My speed must equal 10. This beast here, this is Vx squared. This is Vy squared. This whole thing is Pythagorean theorem. So thanks to Pythagorean theorem. Now, I guess here's my game plan. Solve for t. Solve for t. Solve for t. Then use this t to find oh, that's it. Then you're going to be done. Solve for t and then pat yourself on the back. That's what we're going to do. I thought we had to find something else. But solve for t. All right, so this is a little bit of algebra gymnastics. This is a common algebra text. You know what I'm going to do? I'm going to square both sides. So if I square both sides of number 10, my left side becomes 100, because 10 times 10 is 100. If I square the left side, that equals 100. If I square the right side, I get 5.5 t minus 5t squared, quantity squared, plus 81. 9 times 9 is 81. That's my step 13. Here's my step 14. 100 minus 81 equals 5.5t minus 5t squared, quantity squared. 100 minus 81 is 19. So my left side now is 19 equals, I guess I'll repeat it, 5.5t minus 5t squared, all of that squared. I'm going to square root both sides. Ready? The square root of 19 equals plus or minus the square root of 5.5t minus 5t squared. And this is Pythagorean theorem. I'm sorry, this is quadratic. This is a quadratic function. So here's how this boils down to me. I'm just going to say this. What am I going to say? I'm going to say, I'm just going to look at the positive root. I'm going to look at what happens if I just take the positive root. So if I just call that positive, I'm going to have the square root of 19 equals 5.5t minus 5t squared. And at this point, I think you can solve for t. And if I can't solve for t, if it turns out this is undefined, or I get if I get to a point where I'm trying to take the square root of negative number, I know to take the negative root. But go ahead, solve for t, and that will be our answer. I'll use at this point, you should know how to use your calculator to solve quadratics. And definitely speak up if you see me make a mistake in terms of this manipulation stuff. Okay, let's begin. My squared term is -5. My linear term is 5.5. My constant is negative square root of 19. Negative, all right. -4. All right. Oh, get an imaginary, so strike 1 for me. So now I'm back to it. Nope. Take negative root. So instead of looking at the positive root, I'm going to look at the negative root, So then that means I have square root of 19 equals negative 5.5t plus 5t squared. Now, if I solve for t here, square term is 5. My linear term is negative 5.5. And I have negative square root of 19. So what does this equal? 1.6 and some change. Okay. T equals 1.63364. Done. This was part D. What's going on? I'm going to move this. That's better, I think. All right. So we got part A is done. Part B is done. Part C was done somewhere here. This is part C is done. And then in terms of just dense algebra, part D is done. I mean, but the real takeaways are, again, unit vectors, how to deal with unit vectors, specifically how to deal with vectors in general, and basically just, yes, I know velocity is dx dt and acceleration is dv dt. So pretty heavy, easy when you look back on it, but let's see how people are doing before I move on. This was quiz 2, believe it or not. Chapter 4 quiz. Oh, geez, everyone's done. So you're waiting on me. Well, it's embarrassing. No. All right. Just happy to go slow for a while. All right. So let's do quiz 3. Chapter 4, quiz 3. I tell you though, that last, again, it's always the same. Easy to follow the breadcrumbs, hard to actually lay down the breadcrumbs or to create your own breadcrumbs. Chapter 4. Chapter 4, quiz 3. Chapter 4, quiz 3. It's now 2:39. I'll say 3:30. Okay. Chapter 4, quiz 3 is now available. Please let me know if it's not. And now we do a two-dimensional projectile. Okay. And if this method, if this method is any good, we shouldn't have to start from 0. A methodology isn't really valid if you kind of have to start from 0 every time you apply it. So here goes. An airplane has a certain speed and it's diving at an angle. So this is what's going on. This jet is going into a dive. So at this moment in time, I have a vector looking like that. So it's going into a dive, and then it releases a radar decoy. So something's pursuing this jet, and it basically spits out a decoy. So the radar tracker of the other system locks onto the decoy instead of the jet. So it's a way to evade radar detection. Okay, so what do we know here? We know the speed, the diving speed and the diving angle, and then it releases the decoy, and then we know how long is it in the air and how high was the release point. All right, so in terms of the dollar signs, how long is the decoy? T equals $. This is what we need to find for part A. How long was this in the air? And then for part B, Y initial. Y initial equals the $sign for part B. So the kinematics analysis method, you have to go crazy labeling everything. And you got a taste of that last Thursday. So let's label the heck out of this situation. So pretend it's just like an exam, because you will be asked to do exactly this during an exam. And in fact, let me do this. Let me just take a little snapshot here. This is 427. Let me get a better picture. so it's easier for you guys to read. 427. This should look better. Okay, please stand by while I copy and paste this visual onto your screen. And here it is. But I want to make a big deal about this labeling process since it's required and helpful. I mean, I'd like to think that there are no requirements in this class that aren't helpful. None of them are punitive. And I keep saying that because in some ways, every requirement kind of feels punitive to me sometimes. So let's label this. All right, so here's, this is where the decoy hits the ground. This is my initial X velocity. My decoy hits the ground at Y final. My decoy, so here's the decoy itself. I'm just going to indicate this is where the decoy is released, right there. The decoy is released at that point. So this could be my Y initial. So I have Y initial, that's my, and that's a $sign. What else do I know here? A lot of stuff, to be quite honest. So I'm going to, this is two-dimensional kinematics. So you're going to take your pen and draw, this is my X velocity. This is my Y velocity. So in terms of initial velocity, my initial velocity looks exactly like this. Okay. And then let's label it. This is Vx initial. This is Vy initial. X and Y are always perpendicular, so I can draw that perpendicular. What is this here? This is V initial. There you go. All right, so what am I missing? A sub Y equals negative G. This was the heart of, this was the measuring G lab you guys did. And I can write it like this now. Now that you're feeling great about unit vectors, that's a good way to write A sub Y. So A sub Y is negative G in the Y hat direction. Here's something new. A sub X equals 0 meters per second squared. And I'm writing down A sub X equals 0 meters per second because there is no horizontal acceleration. There is no horizontal acceleration. Why not? Why is there no horizontal acceleration? Because there's no horizontal force. And you could say, yeah, there's friction. We're ignoring friction. There's no horizontal force. That's why. That's why A sub X equals 0. So whatever the starting out velocity is in the X dimension, it never decreases, it never increases, it stays whatever it is. In this case, it stays at Vx side. So this is a lot of good information. Let's do kinematics. And so we're done with the drawing, kinematics analysis method. Let's do the 6-column table. That's next. Ready. It's two-dimensional kinematics. X initial, X final, Vx initial, Vx final, A sub X, and T. And repeat that for Y because it's two-dimensional. It's moving vertically and horizontally. It's moving in the X dimension and Y dimension. Y initial, Y final, Vy initial, Vy final, A sub Y, and T. So now let's just fill in the table. To me, this is downright fun. It's actually it is a little bit addictive. What's X initial? 0. So this is where you can be clever. What's X final? X final is given. X final equals D. So they do give us X final. They give you this variable D right here. For me, it's 668 meters. 668 meters. What's Vx initial? You know what that is? I better switch pens here. In fact, I'm going to move over. So it's trig time here. I'm going to space this out a little bit better. Because we do have to do trig. Here is Vx initial. Ready, set, go. It's V cos theta. V cos theta. V sub VXF. Well, if there's no acceleration, then the decoy does not speed up and it does not close down, does not slow down, I should say, because A sub X is 0 meters per second squared, because there are no horizontal forces. Time is a dollar sign. So let's talk about this. Before we move on to the Y data table, I'm just saying, hey, look at this triangle. Look at my velocity vector once it got decomposed. So this is initial velocity decomposed into an X component and a Y component. Anytime you have a two-dimensional vector, decompose it. And I know because X and Y are always perpendicular, I get to use right angle trigonometry. So ask yourself, in terms of that triangle, what is the cosine of theta? It's adjacent all over hypotenuse. So that's why I'm saying Vx initial equals V cos theta. That's why I'm saying that. All right, so I think we're good to go. I think I'm good to go at least on the X data table. Here's the Y data table. Y initial, that's my dollar sign. That's my second dollar sign. Y final 0, it hits the ground at Y equals 0 meters. Ready? This is tricky. Brace yourself. Minus V sine theta. So easy to make mistakes there. And all I'm saying again, I'm going to go back to this triangle and say, well, I know sine theta is opposite over hypotenuse. So that's why I'm saying Vy initial equals V times sine theta. But I'm adding a negative because the way my drawing is set up, the situation, this is the difference between physics and math. I actually have to be aware of the physics of the situation to say, well, okay, this is falling. This is heading towards the ground there. Okay, next I'm going to erase this. Okay, that's why I wrote down negative V sine theta. Vy final is I don't know and I might not care. So if there's a chance I might not care, I'm just going to give it a question mark. This is negative, let me change markers. This is G, this is what you figured out last Thursday. This is negative 9.8 meters per second squared. And yes, this is dollar sign. So, all right, done with the drawing. Done with the 6-column data table. Next up, well, really, technically speaking, next up, is this constant or variable acceleration? This is constant acceleration. It's not variable. How do you know it's constant? Here's why. You know it's constant acceleration because A sub X is a constant and A sub Y is a constant. A sub Y is negative 9.8 meters per second squared. So because A sub X is the constant and A sub Y is a constant, A is going to be a constant and it's constant acceleration kinematics. So let's play the Big Five game, which is next. I guess number 1. Big Five game. Which variable contains your dollar sign with all other variables known? Let's see here. I'm looking at my data table. I do know V. All right, so it looks pretty easy. Is it? Is it really? I don't know. I'm going to try this. I'm going to try X final equals X initial plus Vx initial times T plus 1/2 A sub X T squared. All right. So let's process that. I'm going to try that. I'm not giving up on it yet. I'm always kind of pessimistic, but so far, so good. So X final, I know X final equals X initial. X initial was equal to 0. So this is equal to 0. And A sub X is 0. So you know what? This all of a sudden, look what happens between step 2 and step 3. X final equals Vx initial, which was V cosine of theta times time. And I'm good to go because now I can see if I'm trying to solve time here, time of flight time. If I'm going to solve the flight time here, I can see that flight time equals XF, which I know, all over V cosine theta. So, and let me know if I'm making a mistake, but according to my data table, XF right here is 668 and V is given. So I might have to do some conversions though. So here's what I'm going to do. A little sidebar, little velocity sidebar here. 200. If I write V without a vector, you could actually refer to that as speed. But for me, this decoy was dropped when the airplane was going 255.9 kilometers per hour. So let's convert that to meters per second. Why do I know to do that? Because I know I need to be dimensionally consistent. I know G is 9.8 meters per second. So I'm going to multiply by 1,000 meters per 1 kilometer. So that takes me from kilometers to meters. Now I need to go from 1 hour to 3,600 seconds because there's 60 seconds in a minute, 60 minutes in an hour, 3,600 seconds. And I'm going to stick this in calculator memory location A. Okay. So in fact, okay. So let's see what that is. What is 255.9 times 1,000 divided by 3,600? Store alpha A. I'm going to just repeat it. 255.9 times 1,000 divided by 3,600. And I'm getting the same answer twice. All right. So here goes to continue. It's 668 with my numbers, 668 meters per meter, 668 meters divided by V, which is sitting there in calculator memory location A, times the cosine of that angle. And that angle for me is 34 degrees. So flight time for me, unless I made a mistake, 668 divided by alpha A divided by cosine of 34 equals 11.3 and some change. 11.3 seconds. And I better put that in memory location B. Store alpha B. Okay, alpha A. Okay, good. That's it. That's $1 sign down, 1 to go. What was the release point? Now, hopefully, at this point, you might actually start to see the sort of the repetition, because it's easy for me to understand how you might be looking at all this and you're thinking, everything is brand new and unique. How the heck could I ever do this? And the answer is, it's not an infinite number of problem types that you need to deal with. You need to deal with, relatively speaking, a pretty small number of problem types. It's not that hard, again, if you practice. To find, let's find release point. Where did the jet release this decoy? That's part B, which means what Y initial is the $sign as mentioned. So I'm going to play the Big Five game again. Play the Big Five game with Y data. Play Big Five game with Y data. And I have a very full Y data table. In fact, now I can actually say, well, I do know time. This is sitting here in memory location B. So look at my Y data. There's a lot of it there. So number 7, which of the Big Five equations contains the variable you want with all of the other variables known? And I'm just going to try this. I want to guess I want to do as little work as possible. All right, so here's my guess. Y final equals Y initial plus VY initial T plus 1/2 A sub Y. That doesn't look too simple, but it is what it is. So if I process number 7, Y final is 0. Y initial is my $sign. So I'm just going to leave that as Y initial. plus Vy initial. And Vy initial is that negative alpha A sine theta. Sine for me, sine of 34 degrees times time, and time is sitting there in memory location B. So this is why we like to store stuff in calculator memory. Plus 1/2 a sub y, negative 9.8 meters per second squared times t squared. Look at that. And let me just look at this because there's a lot going on here. 0 is y final, just looking at my data table. So let me just do a sanity check. 0 is y final is 0. Y initial is the $sign. Vy initial is V sine theta, negative V sine theta. Okay. And is that is still sitting there in my memory location? It is. Times time. Time is sitting there in memory location B. Okay, I think this is good to go. Let's try it. Solve for y subscript I. Solve for y subscript I. Make sure you're in degree mode, not radian. Okay, 1080 and some change. And that is the answer to part. That's the release height. That is the decoy's release height. Okay. Let's see how everyone's doing. That's it. Okay. Gradebook says Chapter 4, Quiz 3. No one's done, so I need to do this. There's everything you need. It is now 2:59, so I'll do this. See you at 3:08 p.m. There. See you at 3:08 p.m. for, I believe it looks like this. You can tell me if it doesn't. It's another, so this is another 2D projectile. So this is technically a special class of kinematics. Let me just jot down the special classes. We've hit on all of this. So nothing new. Again, pretty soon, you guys, you're going to be surprised how soon the time comes when there's nothing new. Here's some special cases. Free fall. Free fall is a special case of kinematics. Here's another special case, projectile. Something flying through the air in 2 dimensions, projectile motion. We ran into another case called parametric motion. So these are kind of special cases. The bottom line is we are still living in the world of kinematics, whether it's 1-dimensional or 2-dimensional, whether it's calculus-based or algebra-based. Free fall is a special case. Projectile motion is a special case. Parametric equations are a special case. So let's just keep going. Here goes. This is clearly right away by you can see immediately this is a two-dimensional projectile. Projectile means something's flying through the air in 2 dimensions, subject to only the Earth's gravity. That is the definition of projectile motion. So it's a 2D projectile, which means acceleration equals constant. Why is the acceleration equal constant? Because of the following. Because if it's flying through the air, it's subjected to only a sub y equals negative 9.8 meters per second squared in the negative y direction, and a sub x equals 0. And feel free to ask again. No question. Every question is helpful. Like, why is it negative 9.8? Where did that j hat come from? Why is a sub x equals 0? Why am I saying I hat? So just always if you have to ask that question 5 times, that's actually a sign of mental health, because you just keep asking the same question over again, and maybe you weren't the one who asked it before anyway. All right, so I'm going to play the big 5 game. I'm going to apply CAM. This is a job for kinematics analysis method, which means I label the heck out of everything. Okay, so I'm going to clear this away because I want to spend a lot of screen space to labeling my critically important diagram. It all flows downhill from the diagram. So here goes. This is, in fact, I'm going to do the same thing again. Let me get a better picture of this 428. I want to get a little bit better picture, and I have it right here. Take up a lot of space with just the drawing. Okay, so again, maybe a little bit better to look at here. That's good. So let's label. Let's go crazy labeling things. This would be my initial. V subscript I is the initial velocity. Rule of thumb, always decompose 2D vectors. Always decompose 2-dimensional vectors. So that light blue vector is a 2-dimensional vector, so I'm going to decompose it. Here's the x component. Ready? It's right there. That's the x component. Here's the y component. Right there. Oh no. Please stand by while I restart and reshare. Okay. All right. So let me try that again. And my y component vector looks like this. Okay. Label. Adjust. Fine tuning here. Okay. Not like that. Taking a crazy amount of care for this drawing because it's important. So this would be my initial x velocity, Vxi. This would be my initial y velocity, Vy initial. That's my initial velocity. Now let's see here, still labeling some things. You know what I'm going to do, just because, let's see, find the height of the cliff. Find little h. Find little h, okay? So my object starts out here and lands here. Okay. So the question is, what's the height of the cliff, knowing what we know about this? So I'm still in labeling mode. I'm going to label this over here. This is my final x position. X subscript f. This here is my initial. This is my initial x position. My initial y position is right here, x or y initial. So it's starting from the ground. So I'm going to call that 0 meters. And I'm just going to call this 0 meters because nobody said otherwise. Nobody gave me any number on that. So I'm just going to call it 0 meters. I'm going to say a sub y equals minus g in the y direction. That's the j hat. A sub x equals 0 meters per second in the I hat. Oh, let's talk about a landing vector. Here's the landing vector over here. So this object hits the cliff over here with this velocity. I'll just do it like that, I suppose. That's a 2D vector. So your rule of thumb comes into play. If it's a 2D vector, decompose it. So this would be my x component. This would be my y component. Okay. And let me line things up. Good enough. This now here's this is Vx final because that's where my interval ends. This is the end of the interval that I'm working on right now. This is Vy final. So it's a lot of good stuff. Here's maybe I'll call this theta final. Okay. So spending again crazy amount of time setting up the drawing. Let's do the 6-column data table. Two-dimensional motion means I have x initial. Let me get rid of this. So this is part of your recipe. X initial, x final. Vx initial, Vx final. A sub x and t, same for y. Y initial, y final. These are the same 6 all the time. Just subscripts are important. Vy initial, Vy final, A sub y, just like this should have been A sub x and t. Let's fill in the table what was known. Then let's read this. It's projected at this cliff. I do know the initial velocity. I do know the angle. And I do know time. So right away, that catches my eye. The stone strikes at A. The stone strikes at point A, which is the landing point, 5.66 seconds after launching. 5.66 seconds. That's true for X. That's true for Y because time does not depend on the X or Y direction. So the stone strikes point A, which is the top of the cliff, 5.66 seconds after launching. I know all this good stuff. Find little h. So let's see. X initial is going to be 0 meters. Y initial, starting from the ground, let's call that 0 meters. X final is I don't know, and I might not care. So that's going to get to be a question mark. Okay. Y final is little h. This is the $sign. Y final is the height of that cliff. That's the $sign. Vx initial is going to be V cos theta. This is going to be V sine theta. And let me just do a little a trig sidebar there. If I look at this triangle right here, I can see that cosine of theta equals side adjacent, which is Vxi over the hypotenuse. And that's why I'm saying Vxi equals V cos theta. And similarly, I know right angle trigonometry says sine of theta equals opposite Vy initial over V. And that's why I'm saying Vy initial equals V sine theta. Okay, what about, I can say this about final X. Because A sub X is 0, this object does not speed up or slow down in the horizontal direction. That this is the same. This is going to be V cosine theta. This is negative 9.8 meters per second squared. This is Vy final. This is, I don't know, but I do have to find that out. I can see for part B. All right, so let's see. The stone strikes point A at 5.66 seconds after launching. Find the height. So I just want to make sure I have all my $signs. That is for sure a $sign. Find the speed of the stone at impact. So this is a $sign. In fact, I already know it. And this is a $sign because I have two contributors to speed, an X component and a Y component. and the maximum height. So I'm going to actually, maximum height's not even here. I'm going to come back. So part C is going to be another chunk of work, but there is my 6-column data table. Let us begin, shall we? Number 1. So at this point, you guys, I'm kind of hoping this is going to look, it's going to, hopefully I'm getting a few figurative nods of that. Okay, I see the method here. It's 6-column data table. No, we did the 6-column data table. It's big 5 time. And again, all of this was preceded by an enormous amount of time and care spent on this drawing, labeling the drawing, all 12 kinematics variables, 6 for X, 6 for Y. Which of the big 5 contains the $sign with all other variables known? And I'm after, I guess, little h. So I guess I'm looking at little h. This is for part A. Do I know theta? Yes. Do I know V? So I know that. Okay. So here goes. Seem to be using this one a lot. Y final equals Y initial plus VY initial times time plus 1/2 A sub Y T squared. Let me just say this maybe one last time in your life because it does get repetitive. This was derived. This was derived in the lecture video. You should have that very well digested. If you're going to be on an engineering path or science path, you've got to be that person. All right, so let's solve for Y final, number 3. Y final equals Y initial, which was 0, plus VY initial, which was V sine theta. What's V? 42 meters per second times sine of that launch angle, which was 61 degrees, times time. So that's VY, and here's time, 5.66 seconds. I'm leaving off the units, I guess. Nah, yeah. Fine. Seconds, and this was meters per second. Plus 1/2 A sub Y is negative 9.8 meters per second squared times time, 5.66 seconds. So let's get the right answer or come up for error and debug it if there's a mistake. Okay. Try it. 42 times sine. Forgot something here. This should be squared. Typo alert. Okay. So note that typo, you guys. I forgot to include this squared here. All right, so I get Y final equals 50.94 and some change meters. Store in calculator memory location A, just because you never know. Store alpha A. That's the answer to part A. Part B says, what is the impact velocity? So we are after this vector right here. This vector is called V final. And you can see, again, based on prior conversation from just minutes ago, V final is going to equal Vx final squared plus, Vx final squared plus Vy final excuse me. This is a job for Pythagorean theorem. So again, I'm circling this triangle. I know X and Y are perpendicular. That's why I can show this as a right angle. And because I have a right angle triangle, I get to use right angle trigonometry, which includes Pythagorean theorem. But from a vector point of view, right here, you guys, right here, I would say V final vector equals VXF vector I hat plus VY final vector J hat. So this is my X component. This is my Y component. We are after the speed, so that's why it's VF, not vector VF. So let's go ahead. Let's plug in. Can we speed of the stone? Oh, you know what I need to do? I need to find VY final. Find VY final. Find VY final. So I think that's easy enough. Play the Big Five game again. The Big Five game is which of the Big Five equations contains the variable you care about, which is the $ variable, with all other variables known. And the next step is just to look at your data table, look at the Y data table. I know all of this stuff, and I'm after VY final. So if I know all of that stuff, I'm going to say VY final, this is my guess, equals VY initial plus A sub Y times T. This is yet another one of the Big Five. This was derived in the green sheets in the lecture video. You should know that derivation. Let's plug in numbers here. And this is, let me fix this. There's a little bit of a typo here. This is VY final. Okay, so number 8, ready. VY final equals VY initial, which is V sine theta. Just looking at my data table right here. Right, there's VY initial plus A sub Y times T. I know all of that stuff. I know that this is going to be equal to 42 times sine of 61 degrees plus A sub Y, which is a negative 9.8 meters per second squared times 5.66. I'm leaving off the units. I'll let you do the dimensional analysis. In the interest of brevity, let's just get a value. 42 times sine of 61 minus 9.8 times 5.66, negative 18 and some change. So VY final, I'll call that step 8, step 9, step 10. I get a number of negative 18.73. This is a job for calculator memory location C. I'm going to double check store alpha C. So again, 42 times sine of 61 minus 9.8 times 5.66 minus alpha C, just to check. Okay, and that's it. Now back to number 5. So step 11. I'll go up here, all the way up here. Step 11, back to number 5. Back to number 5. Here's number 5. Number 5 said your speed, V final, equals Vx initial. Vx initial was, did I write that down? Well, it's just V cos theta. So you need to take V cos theta, square it, plus Vy final, square it, and then square root the whole thing. And let's just double check, because again, this term back to number 5, yeah, this is VXF. How do I know that? I'm looking at my 6-column kinematics table. And this is that is VY final squared. And I just figured out VY. I have that sitting there in calculator memory location C. So let's get the right answer. Speed, which is VF. Okay. 27.6. That is the answer to part B. Done with part A, done with part B. That is part B, sitting right there. Part A went somewhere. Where did I put part? The little h. Oh, I erased little h, I guess. Okay. So little h is in the books. 1, 2, 3. Oh, no. Sorry. It's right here. Little h. And that was part A. All right. Now, oh, this is getting kind of, let me make this a little bit bigger. Okay. All right. I'm going to move that here. Part C says, what was the maximum height reached above the, so what's big H? What's big H? What to do? Big H. Okay. I know. Well, I think maybe I know. I'm going to try this. Number 13, number 14. Number 14, find big H. The maximum height reached above the ground. Find that big H. This is our last task for this problem. So I'm going to do another data table. And it's good repetition. Ready. Here goes. X initial, X final, Vx initial, Vx final, A sub X, and T. That's my X dimension. Here's my Y dimension. Y initial, Y final, Vy initial, Vy final, A sub Y, and T. Let's fill in this table. I'm starting at 0 meters. So I'm just going to go unit. I'm going to leave off all the units. Let you guys handle the units. I'll stress dimensional analysis again and again. X sub F. I don't know. I don't know XF. So that's a question mark. VXI. I do know that this is V cosine of theta. This is also V cosine of theta. This is 0. And this is I don't know. So there's I'm not getting a lot of warm and fuzzy feeling from my X data table, but I'm after big H, which is a Y dimension. So if I look at my Y data table, Y initial is 0, Y final is big H. Because again, I'm not going to point, I'm going here. I'll just call this maybe point B. So my projectile is not landing at point A. I'm looking at my projectile when it hits point B. That's what part C of this question is asking for. Vy initial is V sine theta. Now here's something new and interesting. Vy final is going to be 0 meters per second, because at B, little sidebar here, at point B, Vy equals 0. And then you could also say Y equals Y max equals big H. Good to know. All right, so that's why that's equal to 0. This is negative 9.8, and this is I don't know. All right, so can I get anything here? So there's my data table. That's my data table. So if I look at my data table, it's time to play the big 5 game. Y final equals Y initial, Vy final squared. All right, I'm going to try this based on what that data table looks like. And I guess I'm going over here to step 15. Way over here. Play the big 5 game. Play big 5 game. Which, let me say it. Which of those big 5 equations contains the $sign with all other variables known? And sometimes the answer is going to be none of them, and you just have to do some more cleverness. But let me see here. If I look at what I know and what I don't know, I'm going to try this. I don't know time. I'm going to try the following. Vy final squared equals Vy initial squared plus 2 a sub y final minus y initial. All right, so let's see. This is just a guess. So this equation was derived in the lecture video. You're going to write all of that derivation down on your green sheets. That's where this comes from. Let's see what we know and what we don't know. Do I know Vy final? Yeah, that's equal to 0. It's at right here at the apex. At that moment, there is no y velocity. Do I know Vy initial? Yeah. This is just going to be V sine theta. A sub y is negative 9.8 meters per second squared. Do I know y final? That's big H. Do I know y initial? Yeah. So I think this is solvable. So I think playing this big 5 game the way I did, I can say number 17 is just say solve for big H. Let us solve for big H. Don't forget to square this. This is, I mean, I wrote it down like this, but this is V sine theta squared. Okay. So let's solve for, oh, yeah, big H, which is y final. I did indicate that. Okay. Numbers. All righty then, 68.8. And that's the answer to part C. And we're done. Let's see how people are doing. Time check. 3:39. Chapter 4, quiz 4 is this? Okay, so you guys, more time, spend some more time. More time is needed. Speak up if you have questions. Let me know if you see any mistakes. And I will go into hibernation modes for a minute. Well, I'll start the next quiz up. Quiz 5.
I have a question. Are we squaring it says V sine theta? We're squaring the whole thing. So 49 times sine 61, right? Squared.
Yeah,
Yeah, go ahead. Go ahead and answer.
Oh yeah. Just do that. That number times the sine of like whatever your angle is, and then square that whole number, and then divide that by your 9.8 times 2, which is
Oh, we're dividing the fuck?
19.6. Like 19.6.
Right.
So.
All right. So one last look at the grade book. Chapter 4, quiz 4 looks pretty. There's still some people, but let's move on. And again, maybe let's see what time is it. 3:45. This, depending on how long it takes, this might be our last quiz of today. Maybe not, depending again on
Nice. Thank
the
you.
amount of time. But we'll again extend whatever needs to be extended. So you should see quiz 4. I'm sorry, chapter 4, quiz 5. Chapter 4, quiz 5 is now available to you in Wiley Plus Okay, so let me share. Chapter 4, quiz 5. Let me know if you're not seeing what's on my screen. A rifle shoots a bullet to be aimed at a target 46.7 meters away. If the center of the target is level with the rifle, how high above that target must the rifle barrel be pointed? So the bullet hits dead center. So here is a projectile. This is two-dimensional projectile motion. Here is a projectile. That's a projectile. Over here, way over here, is a target. So here's the target. This red. Here's the target way over here. There. That's the target. Okay. So it says this target, the center of the target is level with the rifle. So let's indicate that. Let's make sure the drawing's accurate. Here's where the projectile leaves the rifle. And at that same height there, you have the bullseye. That's the red dot is the bullseye. This rifle shoots bullets at 473 meters per second, aimed at a target 46.7 meters away. So relentless adherence to cam. Let's go crazy with the fully labeled drawing. All right, so this would be X final. This would be Y final. This would be X initial. This would be Y initial. And then you have to, if you're going to hit this target, you're going to have to give this projectile an initial velocity. And your initial velocity is something like this, like that. Okay, this is the initial velocity. You have to point upward. And right away, you should say, oh, that's a two-dimensional vector. So I'm going to decompose it. I'm going to decompose all two-dimensional vectors into components. So this is the X component right here. This is the Y component. Let's label things. This is Vx initial. This is Vy initial. This is my launch angle, theta. The bullet, once launched at that angle, the bullet's going to go flying through the air along this parabolic path and hit. Let me try that again. It's going to go flying through the air. Not good enough. I'm sorry. All right, here. There. Good enough. There. It's going to follow this trajectory. This has a name. This is called the trajectory. So this yellow dotted line is known as the projectile's trajectory. Special word. All right. What does that angle need to be? Okay, so I don't know. And actually, let me check your green sheets. Let me just go into the green sheets, the physics 211 notes. This is chapter 4. I need to double check. I need to remind myself what I derived and what I didn't derive. So here, this is just so you can see what I'm doing here. Well, you are seeing what I'm doing here. All right, so there's all that good stuff. Motion graphs, fine. 2 and 3D kinematics, fine. There's our projectile motion. 5 of 7. 6 of 7. So you guys actually have this. Well, that's interesting. I wasn't quite sure if you did or not. But I guess, you know what? I was going to do things maybe the harder way. And I love the expression, if you ever have a choice, do things the harder way. But I guess this would be the harder way. In your green sheets, you do have this page called Time to Derive the Range Equation. So the word range is very special. It means the launch height is the same as the landing height. And that's what it says right here. So you know what? You need to make sure you understand all 5 of these boxes. And you need to make a list, like literally in your notebook, make a list of questions you need to ask me or someone else about something you saw in the lecture video that doesn't make sense to you. Because in box 5, we have something called the range equation. Okay. All right. So I'm gonna copy and paste box 5 there, the result that you see there in box 5 right here, because we do have a range situation. We have a range situation because, as mentioned, number 1, y final equals y initial. So this is good to go for range equation. And the only reason I keep saying, hey, understand these derivations, because what if you kind of need to rederive some stuff during an exam? Just seeing how stuff is derived makes you a better deriver yourself. All right, so I'm thinking range equation because my launch height matches my landing height. All right, so I guess I'm gonna find theta, number 2. Can I, why? I can, I suppose. Find theta. If I can find theta, then I can use trig to find out the point I'm aiming at. And I better indicate that here. It says how high above the target. So here's my aim point. I'm going to aim. I am aiming my projectile at this point. Ready, set, go. I am aiming right there, right about there. So this big purple dot right here, this is my aim point right there. I'm just going to tidy up a bit here. All right, so I am aiming here, aim here. Okay, that's what I have to aim at. If I aim at that point, my bullet will hit my projectile will hit the target. So that's why I'm saying let's find theta, because that's my aim point and this is the height, because it says where do you have to aim? Directly above the target. So that's what I'm drawing right here. This is the point directly above the target. So let me just fine tune that just a wee bit. I'm going to bring this over to there. That looks even better. That's it. Because again, it said the aim point was directly above the target. That's why I just did this little adjustment. And this number right here is your dollar sign. This is whatever. I'm just going to call that Y for the time being. All right, so find theta. If I can find theta, I can find that green, that light green triangle. So ready, here goes. Start with the range equation. R equals V initial squared times sine of 2 theta all over G. We got to get theta all by itself. So you know what? Let's get theta all by itself. So that means G times R all over VI squared equals sine of 2 theta. And that means the following. That means, well, I'll do it like this, equals sine of 2 theta. Or what if I just say equals sine of, what's a nice number to use? Sine of angle A. Sine of angle A, where A equals 2 times theta. I'm just doing it like that because I want to be able to say this. A, whatever that A angle is, it equals arc sine of GR all over VI squared. So you're going to get a value for A, as you see there in step 5. In step 6, you're going to say theta equals A over 2. In step 7, now that you have this value here, you have, this is X and Y are always perpendicular. So look what I'm doing to my right angle triangle here. All right, I know everything I need to know. This dimension right here, this leg of the triangle right here, This is 46.7 meters. For me, this angle is going to be whatever you get from step 6. Solve for y. Solve for y. Okay, let's do that. G. And remember, this is just, let me just throw this here. G always equals 9.8 meter per second squared. Don't confuse that with, sometimes you're going to say a sub y equals minus g equals minus 9.8 meters. So that might be true in some cases, but g itself, this variable g right here, is always equal to 9.8. Just throwing that out there. Okay. Okay. 2. I'll add this here just for. That's the answer. I guess that's our only answer. I'll be back in 2 minutes.
Okay, let's make sure I got it right. G is 9.8. R is whatever my range is. Then divided by whatever my velocity is, right? Squared. Why the fuck is it not giving me that? Divided by
What'd you
2.
say?
I said G is 9.8. R is
Yeah.
my range,
Yes.
right? Divided
Mhm.
by my initial velocity squared. Right. And then
So, are you looking for A or are you looking for theta?
I'm looking for A right now.
So yeah, it's gonna be the arc sine, and it's gonna be yes, your range times your 9.8, and then over your um uh initial velocity.
Are we back in radians? Is that what it is?
Degrees.
Oh, degrees. Okay.
Yes.
Oh, thanks.
Okay, so how's it going, everyone? Let me check in with the old grade book. This was chapter 4, quiz 5. Chapter 4, quiz 5. No, this is we need more time. We need to spend more time on chapter 4, quiz 5. Okay. So let me go back to the notebook here. All right, so when I did this, okay. So step 4 is good, hopefully, to go. Step 4 is making sense, I think. Step 5, you solve for A using arctan. So when I did that, I said I'm looking at step 5, 9.8 times 46.7, which is that big R number, which stands for range. My number is 46.7 divided by 473 squared. All right. So you know what this is coming down to? This is saying, hey, this capital letter A is going to be the arc sine of a really small number, 0.00204, on and on and on. So make sure you're in degree mode, not radian mode. So with this number just sitting there, I'm going to write it down, I guess, right now, but normally I'm just going to keep this number in the calculator. So the arc sine of that number, inverse sine of that number is A equals the inverse sine of this argument. So it's going to be 0.11.
According to Byju's,
72.
arc sine is the
My phone thought I was talking to it. 0.1172 and some change. So that's equal to A. And based on step 4, because I did this, I'm going to say, well, if A equals 2 theta, then theta equals A over 2. So if A is 0.1172 and I divide by 2, I get this number. Theta is, so that's a very, very small degree, 0.586 and some change, 0.586 and some change. So that's theta. And then once again, step 8, I'm saying, well, all right, I know right angle trigonometry. I know the definition of tangent is opposite over adjacent. Opposite is y. Adjacent is that 46.7. So then I'm just going to say y equals 46.7 times tangent of theta of that 0.0586. But again, I know just to recall that from calculator memory. So tangent of that angle times 46.7 is equal to just about 4.6 centimeters, or in terms of meters, 0.04776 meters. So that's the nitty gritty how I get this answer. So finish that up. Let me check again on status. This is quiz 4, chapter 5. All right, so a few more. That's good progress. Let's do, because it's 4:06, let me take a look at chapter 4, quiz 6. And let's just see how time consuming that looks. That does not look too bad. All right, one more quiz. Let me make it available. Chapter 4, quiz 6. One moment while I make it available.
Could you go back to quiz 5?
I will. Let me first, let's get started on quiz 6. And again, I'll backload this. Chapter 4, quiz 6. Last quiz of today. We should finish pretty soon. Chapter 4, quiz 6. Let's see. This is us. It's now plenty of time. I'll leave more than enough time for quiz 6. Okay, so right now, you should see chapter 4, quiz 6. Let's knock this down. Because again, you guys, I think we have our arms around things. It might not feel quite yet, but it will. But I can go a little bit faster here because I think there's not a whole lot of, we've covered the method. So I don't have to explain the method. I can just start applying the method. So let's go right into application. A golf ball is struck at ground level. So now we have a graph though. All right, so A, how far does the golf ball travel horizontally before returning to the ground? Interesting. So number 1, well, let's do the picture. Here's my golf ball. This is my golf ball sitting right here. Let me make sure I'm showing. Okay, my golf ball is given some initial angle, some initial launch velocity. This golf ball flies through the air like this and comes back to the ground. So this is another range situation. So maybe we can reuse that range equation. All right, but we have to fight the good fight. This is going to be my initial launch velocity. Do I know how far does the golf ball travel horizontally? What's the maximum height? So you see a two-dimensional vector, and right away you know to decompose that into components. This is my x component. That's my y component. Vx initial, Vy initial. Golf ball flies through the air. So it starts at x initial equals 0. It ends here at x final. X final, I'm gonna say x final equals range. Okay, so how far does the golf ball travel horizontally? So this is a range situation. So number 1, this is range kinematics. I'll put it like that. This is range kinematics. Why am I saying it's range kinematics? Because y initial equals y final. The launch height is the same as the landing height according to the problem statement. A golf ball struck at ground level. How far does the golf ball travel horizontally before returning to ground level? That's my justification. So I'm just going to go back to this, take a copy of the range equation, which is right there. Can we reuse this? Is it going to be kind of that easy? Well, let's see here. No, it's not going to be that easy because I don't know theta. So number 3, I don't know theta. I don't know theta. It was too good to be true. This is theta up here. So here's theta. That's what it looks like. I just don't know its numerical value. So number 3, let's examine the graph. Examine graph. And there's always, graphical analysis is a really big deal. When I look at this graph, I'm kind of look at some points that are like, here are the obvious points. This is an obvious point. This is an obvious point. This is an obvious point. So you look at the obvious. You look at the crispy intersection points. So you would look at where does y equal 0? Where's x equals 0? You look at slopes. You look at area under graph. So area of v versus t maybe. So you look at sort of a standard suite of properties when you look at a graph. All right, so from this graph, if I examine this graph, what can I say? What comes falling out from this graph? Well, I can see right here. I'm going to see right there. This for me, this is 2.5 seconds. That's a pretty noteworthy point. Number 5. Different pen. For me, at that inflection point at t equals 2.5 seconds, I can say this. I can say the following. V y equals 0 and y equals y max. Why am I saying that? All right, because I have VB here and I have VA here. And at 2.5 seconds, at t equals 2.5 seconds, you know what I have here? This is my min velocity. So right here at this point, this is my minimum velocity right here. Okay, right there. This is my minimum velocity. It's not equal to 0. It's just a minimum velocity. So this is V min. Okay, so then that's a big deal. I can use that. Number 6, because V equals, you guys have seen this before, because I have an X component and a Y component. You guys have seen this a whole bunch of times. V equals V min at Vy equals 0. So right here, right at this tippy top point, right here, right at this point, this corresponds to y equals y max and Vy equals 0. This is called the apex. This is the apex point or the peak, the apex or the peak. Okay, right there. So I actually know at that point, Vy equals 0, which means this. Vx equals whatever it says on the graph. Vx equals Va. And for me, Va is given as 18 meters per second. All right, so that's pretty good to know. I know at that particular point, and again, I know the time. So you know what I'm going to do? I guess I'm going to do maybe this is not really a job for the range equation. So just go ahead and fight the good fight. Let's do X initial, X final, Vx initial, Vx final, A sub X and T. It's 2-dimensional kinematics. So I'm going to do Y initial, Y final, Vy initial, Vy. And maybe I can get that range equation to work. But right now, I'm taking this approach. And maybe I'll regret it, but we'll see. All right, so the golf ball, so X initial equals 0. Let's put 0 there. It's starting at the ground. Y final, because it returns to the ground. Good to know. And I'm just going to look at what's going on between what I'm going to call point A and point B right here. What's going on between point A and point B? And I know I'm trying to figure out how far did the ball go and what's the maximum height. So Vx initial, I have that number. Aha. Vx initial is 18 based on this conversation I had in step 6. So this is going to be 18 meters per second. Wait for it. This is going to be 18 meters per second because this golf ball does not speed up or slow down in the horizontal dimension because there's no acceleration. There are no horizontal forces causing or creating a horizontal acceleration. This is 2.5. So look at all that stuff I know for my X data. For my Y data, you know what? I think I can figure out V sub Y. We'll find out. But for now, well, this is going to be negative 9.8. This is going to be 2.5 seconds. This is going to be 0. This is, I don't know, but I think I can get that from the graph if I need to. But for part A is saying, how far does the golf ball travel horizontally? X final equals X initial. Okay, so number 8. For part A, this is what you're after. You're after XF. How far does the golf ball travel horizontally equals $. So play the big 5 game. Let's play big 5. So here's what I'm going to do. I'm going to say X final equals X initial plus, here's one we haven't used too often, 1/2 VX initial plus VX final times time. This is yet another big 5 equation derived in the green sheets, or you write it down in the green sheets after learning it from the lecture video. We know all of this stuff here. So let's go ahead. Step 10, X final equals X initial 0 plus 1/2 VX initial was 18 meters per second plus VX final is 18 meters per second times time. And this is the halfway point. So this is 2.5 seconds represents half the flight time. So that's why I'm going to get an answer here. And my answer is going to be for the half flight distance, 18 times 2.5. All right, so for half the flight distance, this is equal, my calculator says 45 meters. But now this, multiply by 2 times 2. Multiply that answer by 2 because I don't want to multiply by 2 to get full range because 2.5 seconds just yields half the range. So 45 times 2 equals 90 meters. That's the full range. That's the answer to part A. And let me just stress this. When I was using this 2.5, when I was using this, so I really keyed heavily on what's happening at 2.5 seconds. That told me what my initial X, that told me what my X velocity was. It said Y velocity equals 0. So that's the answer to part A by reading the graph the way I did. Part B says, what's the maximum height attained by the ball? So number 11, I'm going to go back to the graph. Back to graph. Because, you know, if I look at time equals 0, look at t equals 0. That's a crispy point. Look at t equals 0. At t equals 0 right here. Right at time equals 0, what's happening at the launch? At t equals 0, my launch velocity is right here, VB. All right, so I'm going to use that. Step number 12 says, again, I'm just looking at this triangle right here. I'm looking at this triangle, and I can see that this launch, how far, what graph? The speed of the ball. All right, so I can say the velocity, thanks to the Pythagorean theorem, is Vx initial squared plus Vy initial squared square root. And I know right at t equals 0, this equals VB at t equals 0. Step 13, therefore, I'll go over here. Step 13, VB for me, is 30.4. So step 12 becomes step 13. 30.4, I'll leave the units off. 30.4 equals Vx initial squared. I got that. And that never changes. That's 18 meters per second squared plus, check this out, Vy initial squared. Okay. Square root. Okay, so let's solve for V subscript Y. So I'm just going to say 30.4 squared equals 18 squared plus Vy initial squared. So step 15, Vy initial. Let's get a number on that and store it. 30.4 squared plus 18, oops, sorry. 30.4 squared minus 18 squared, square root of that. Okay, so Vy initial for me, 24.49 and some change. So now I have this number. I have my initial launch velocity, which is pretty good as far as my data table. Vy initial, I'm actually going to erase this and replace it with 24.49 and some change, 24.49 meters per second. And it's big 5 gain. I'm just wondering, did I even need to do that? I think I did. Vy. Yeah, I think I did need to do that because I just didn't have enough known. So in conclusion, number 16, play the big 5 game. Big 5 game for Y data. If I look at that Y data, I'm looking at that Y data row in my 6-column kinematics table. I'm going to say, because I'm after the maximum height, so I guess I'm going to do this. Oh, I better update this too. So this now becomes Y initial still 0, and this is the maximum. So this is the $sign. So for part B, this is part B. Part B is what is the maximum height above ground level? All of this is good. Okay. Replacing 0 because it's not landing on the ground. I'm stopping the interval when the projectile hits its maximum height, not when it returns to ground level. So that's why I made this little update. So now I guess I'm going to go with Y final equals Y initial plus Vy initial times time. I know all of this, I think. Yes, I do. Good. Plus 1/2 times negative 9.8. Let me stay in equation mode. Plus 1/2 a subscript y t squared. Last step. Okay. Your peak height, which is that Y final going from point A to point B, as you see there with my updated data table, equals Y initial, which is 0, plus Vy initial, which is sitting here in my calculator memory location. Store alpha A. Calculator memory location A times the time it takes to get to that apex, which is 2.5 seconds, plus the 1/2 times negative 9.8 meters per second squared, leaving off units. And I got to give in t squared. Okay, here. Times t squared, which is 2.5 seconds. Squared. Okay, just creeping over. That's it. So let's see, 19. So the peak height times 2.5. It's 4.9 times 2.5. Okay. Y sub f, this is the peak height, equals 30.62 meters, and that is the answer to part B. So my hope is at some point, probably soon, this is going to look comfortable. This is going to start to feel comfortable. This methodology, this approach, because really we've hit it a lot with some good variations. It's not the same thing over and over again, but it's a variation of the same theme over and over again. So that is our chapter 4, quiz 6. This is that's good. Okay, like that. And let's see how everyone's doing. Time check 4:27. I am done. We have covered 6 quizzes, hopefully learned a lot in terms of methodologies and approach and tactics, big picture stuff. You're getting the right answer. Let me check. Let me check on the grades. This is chapter 4, quiz 6. Chapter 4, quiz 6. A good number. So there you got. So at this point, shout out what you need me. What do you want me to reopen? Here, any requests for reopenings?
I need quiz 5.
All right. Quiz 5. Oh, that's I will reopen quiz 5 for, I guess, until 5 o'clock. If there aren't any other,
Quiz 4 too, please.
say again.
Quiz 4, please.
Quiz 4. Okay.
And quiz 1.
Okay.
And that's all.
That's it then. If so right now I will reopen 1, 4, and 5 until 5 o'clock. All right, you guys. I'll leave this on here for a minute. You can drop off when you're good. When you're good, I'm good. But I'm just gonna hang out here and reopen these quizzes. And we'll see you on Thursday.
Bruh. How is this wrong?
Quiz 1, 4, and 5. 1, 4, and 5. One. One is done. Four.
Alrighty. Hey, Professor, I'll see you on Thursday, right?
Yep. Sounds good. Thanks. See you Thursday. That's 4. Good. And here's 5. Okay. All right. All right, that's it for me, you guys. I will see you Thursday. If there's any issues that are plaguing you, just group text me. I got to go do an errand, and we'll see you soon.
See you Thursday.
Yep.
Thank you.
Yep, you're welcome.